So oversampling again as a concept is something very similar. I've already explained to you. In case of undersampling, all we were doing was taking the minority class. We are not basically playing around with the minority class. We took the majority class and somehow brought it down, right? It was through random undersampling, it was through cluster centroid, tomic links. Now in oversampling, the idea is take the minority class and inflate it to the size of majority class, right? So that's the concept. So there's nothing much around it. So now let's see what are the different ways you can do it. So the same example, so from B now. So now you're not going to touch, right? So this was the example earlier. So in earlier, first example of undersampling, what we did was take class A and undersample it, right? So we've, out of 975 points, we basically chose 475 points. In this case, we are going to not touch the minority class at all, sorry, the majority class at all, and we are going to take the minority class and inflate it. So we have 25 points and we are going to now take 225 points, right? And with that we would have a higher proportion of the minority class, right? So again, instead of 225, could it have been 250, could it have been 275, could it have been 450? The answer is you do not know until and unless you test it out, right? So there's nothing which says this is the right amount by which you should oversample, or this is the right amount by which you should undersample. This is something that you should be testing out depending, as in case of undersampling, as you saw, right? The more you undersample, the more chances that something like a random forest or decision tree would tend to overfit on that, right? So that's something of an intuition that you have, but obviously at the outside you just know about that. You really don't know how much undersampling affects the model at what capacity, right? So that's something you have to test out and see. So oversampling, again, same example of oversampling, you're not touching the minority class, so you're not touching the majority class at all, and you're just taking the minority class and just multiplying it, right, somehow. So now the first concept, which is nothing but similar like undersampling, random oversampling, which is basically take samples with replacement, right? So you have this minority class which is small, but I'm going to take randomly samples from it oversampling, and you basically repeat the data points, right? So oversampling, you're basically adding randomly new data rows, right? So oversampling is basically nothing but you're just adding rows, and which are the rows you are adding? Randomly from positive or the minority class, right? So from the minority class, you're just going to take randomly samples and you're just going to add them up, right? That's the concept. So nothing much out there. So you do the same thing, and now you see something which is fantastic. Your random forest has now a much better performance than earlier, right? So it has gone out to 7.78. So now we are going to be talking about oversampling. So now you suddenly see a huge jump here, right? So this is way up than 0.76 and definitely above 0.73. Then now what happened with our logistic regression? Let's see. So logistic regression is almost there also, 0.776, but it's not definitely as good as our oversampling for this is random. So obviously you can see this increase in performance, and why is that so? So now let's see how many data points did we have. So yeah, we had roughly more 350, 700-ish data points, right? So this is somewhere around 750, 700-ish data points. So obviously you fed it a lot more data than you fed it here. So obviously with the increase in data, it got more patterns to learn from. So not only is this an increased data, but this is also an imbalanced data, right? This was an imbalanced data. So this was imbalanced data, and this is a balanced data. Now what happens with case of random forest if it's an imbalanced data is basically, if you remember, random forest was splitting the data into multiple splits, right? So if it's an imbalanced data, the imbalance could basically be multiplied, right? It's amplified. So when you're in random forest, it was splitting the entire data set into multiple splits and training models on each one of them, and then ensembling the decision from all those models. Now if you already have an imbalanced data to start with, if you kind of split it into multiple parts, that imbalance could be further amplified, which is why you see this, right? So even if they are almost similar, or probably this is slightly larger data points, the very fact that this is imbalanced and this is balanced, right, which basically says for the fact that both of them are actually performing much better than, not much better, logistic regression is definitely performing almost similar, slightly better than its corresponding normal version without any pre-processing. whereas random forest is definitely performing better. Obviously, it's performing much better than all of these three techniques because these are undersample techniques. So random forest overfit on all of this. It could not overfit on a larger data set, and obviously this is a balanced larger data set. So this makes it work much better. So now the final concept of oversampling, which is the concept of SMOTE, or it's called synthetic minority oversampling technique. Don't get flustered around with the name. I know the name could be a bit confounding, but don't get there. The idea is very simple. The idea is actually much easier if I'm explaining you with this small example graph. So there are steps to it. The first step is basically you have the entire data set. So understand this graph clearly. So the graph just says that there are positive examples, which are basically your positive or the majority class examples. Positive or the minority class example, which are basically the red ones, and then there are the negative or the majority class example, which are basically the black one, right? So the first example is ignore the majority, right? Because this is an oversampling technique, and oversampling technique basically consists of the fact you have to amplify the number of your minority examples. So all you're gonna do is first ignore the majority of the classes, right? And the next step is you're going to take these minority examples, and for each of the minority examples you're going to find out the nearest neighbor, right? So for example, you just find out the nearest neighbor to this particular example. So this is the one, and you find out its nearest neighbors, right? So in this case, if you want to basically multiply your positive data set, right, or minority class by 3x times, right, 300% you want to amplify so this is the amount of oversampling you want to do. Then you basically choose 3 neighbors, right? So 3 neighbors for this particular data point out of all of this. These are the 3 neighboring data points, right? So now you create a new instance, right? So new instance is basically what we anyways are doing for oversampling. How do you create that new instance? Is basically by creating a point between on each of those 3 lines, right? So you're going to create a point out here, you create a point out here, and you create a point out here, right? So that's the whole concept of SMOTE or oversampling techniques. It's basically first you take the minority class, and now for each point in that minority class you figure out which is the number of, so you basically choose how many times you want to oversample. So if it's a 50% oversampling, or if it's 100% oversampling, 200%, 300% oversampling. So if it's 100% oversampling, then you basically choose the nearest neighbor, and between each point and its nearest neighbor you insert a point in between, right? So let me explain this via graph again here. So for each minority examples, you are basically going to choose, say if you are doing 100% multiplication, so which is basically for every, if your current size is x, you want to go into 2x, right? So if you're doing that, what you're doing is for every point you're going to figure out what is the nearest neighbor, and between that point and the neighbor you're going to insert one single point, right? So which is basically going to be the mean of, it could be the mean of these two, it could be somewhere between any of these 2 lines. So that's the concept. Now if you're doing 200% multiplication, right, so you want to go from x to 3x. So what you're going to do is for each point, each minority point, please keep in mind these are all minority points, all of them are minority points, right? So what you're doing is just taking the minority points, and for each minority points you are basically choosing, in this case, 2 minority points which are closest to this particular point, and for each of these 2 points you're going to insert a point which is between them, right? So this is the concept of SMOTE, and that's exactly what is written out here. So I'm sure now you understand this. So now that you understand, let's kind of go back and kind of explain you what. So minority classes oversample by creating synthetic example, means artificial examples, than by oversampling with replacement, which is a more very naive technique to do. So what it does is it generates synthetic examples in a less application specific manner by operating in feature space rather than data space, which is basically trying to figure out data points which are very similar in feature to your minority class and creating those synthetically, right, rather than trying to create new data points altogether. It basically creates points which are very similar in feature to your already minority features, and that's it. So we have already talked about the rest of the things. So you can basically introducing synthetic examples along the line joining any and all of the nearest neighbors, right? So basically take every minority point and basically figure out which is the line joining that point to its nearest neighbor, and between all of those points you basically insert a new example, right? That's as simple as it is. So I've explained you this. So I've already explained you this. If you are doing 200% oversampling, then you are, for every minority point you are going to take two nearest neighbors and insert points, 2 points between each of those lines, right? That's the concept. So now let's try and understand how SMOTE performs as compared to the other oversampling technique, random oversampling. So in this case, as you can clearly see, random forest did not perform as well. So 0.758, which is roughly 0.76 again here. So this is SMOTE. And 0.778, which is roughly 0.78 for logistic regression. So in this particular example, as you can clearly see, SMOTE did not help a lot, but that doesn't mean SMOTE is not really effective. It's just that in this particular data set, probably the data was not rich enough, as in the feature space, it was not rich enough to kind of, even if you do SMOTE by adding a lot of data points, that is not really probably adding a lot of information, and that's why you probably see a not so significant improvement in performance. It's almost similar to what you did here, right, which is without any pre-processing. But please keep in mind, SMOTE is one of the very powerful techniques for imbalanced data set handling. As you already understand by now, undersampling is not the best way out forward, right? Because in undersampling, you are basically losing out on data. You don't want to do that at the outset. So you want to definitely go ahead with oversampling. And out of oversampling techniques, random oversampling is definitely something that works. But even something which is a lot more exotic and sophisticated is SMOTE, and I've already explained you what it is. It's nothing but basically creating, if you have minority data points like this, how do you create next set of points? You say, okay, I'm gonna select these points which are very similar to this, right, but not exactly equal to this. You're not going to take this point and kind of put it here, which is what you are doing in random oversampling. In random oversampling, you have your normal minority data set and you kind of repeated those points over and over again. In case of SMOTE, you're going to not exactly repeat them, but we are going to kind of try and create a replica of those points, as in the terms of points which are similar to points in the minority data points, but not exactly similar. That's the concept of SMOTE. So now that kind of draws us to the end of change the data approach. So change the data approach, frankly, is, now to summarize, consists of two parts, which is change the minority class, change the majority class. If you're changing the minority class, you're basically going to multiply it, amplify it in size. How you can do that? Two techniques: oversampling randomly, or basically doing your SMOTE technique, right, which I have already explained. In case you're doing undersampling, which is change the majority class, you are getting rid of some of the data points from those majority class. How you can do that? You can randomly drop off data points, or you can basically break the entire negative class into different unique clusters and then select a representative from each of those unique points, right? And the third example was basically where we talk about Tomek links, where for every minority class you figure out which is the nearest very similar majority class, and you remove that, such that the decision boundary is much more clearer and it's easier for the model to learn from a clearer data set, cleaner data set, right? So that was the whole concept of change the data. Now we are coming to the second part, which is change the algo. Now change the algo, we are basically going to use something which is I would say which is something which is very intuitive to understand, because we have already covered all of this algorithm. So change the data part was a lot of algorithmic hacks, so a lot of engineering hacks that you could probably think about by yourselves. Algorithmic approaches are something which you would probably can guess if you are very familiar with how the learning of each of the algorithm happens. So we are going to talk about some of them. So the first approach is cost penalized training, right? So penalized training or cost sensitive training. Now this is again as a concept something that we have already talked about in boosting, right? In boosting, if you remember, we were giving each of the data points that were basically classified as incorrectly by first model, we were giving a lot of weightage those points, right? So I had explained then also what does adding weightage do is basically while you are say doing your MSE loss, right? MSE loss is nothing but summation of yi minus y pred I square, right? This is what it was, summation on y, right? So this is what it was, MSE loss. So now let's understand what is a cost penalized training. So in case of example, say in case of logistic regression, if you remember log loss was summation of minus log of p of right class, right? That was the easy way to remember. Otherwise there's a formula which is minus y hat and all of that. So anyways, the point to understand here is this, that in this particular case you can clearly see that, or let me actually write that formula, right? So what does that formula say? It was y into ln of y hat plus 1 minus y into ln of 1 minus y hat, right? So you remember, if y equals to 0, this part goes to 0. If y equals to 1, this part goes for 1. And that was the idea. So now what cost sensitive training means that in case while you are training like this, what it sees as, what you're saying is this, right? So it's all yi. So you're going to sum up about all data points, right? What you're saying is that for each data point I'm going to give equal weightage, right? So for every point it's going to be same, right? And for each of the classes, right? So if it's class 1, this is your cost, and if it's class 0, this is your cost. You are saying they're almost going to be same. But what if you say something like this, say 4 times into yi into ln of yi plus 0.01 into 1 minus y into ln of 1 minus y hat. So this is y hat. Right, so what you're doing right now is saying that if you're making an error on this, right, which is class 1 prediction. So if you're making an error in class 1, so if we remember class 1 prediction, this part goes to 0 and this is a part, right? So if, let's now write it, if yi equals to 1, your log loss is 4 into ln of, it's 4 into ln of y hat, right? If yi equals to 0, log loss is equals to 0.01 into ln of 1 minus y hat, right? Y hat is your probabilities, right? Prediction probabilities. So you can clearly see here, if your class is 1, you're giving a lot more weightage to that particular misclassification, right? So the error that is coming out from class 1 prediction is lot higher if you're making an error here, right? If you're making an error here, you're penalized a lot more as compared to here, right? Because this term is exactly the same. If you're making similar error here, the penalization is much lower. If you're making an error here, the penalization is a lot more. So this is the whole concept behind cost sensitive training, that in case you modify your cost function, right, which is what you had used in logistic regressions, so those are the things that you kind of modify straight up and say that, okay, you know what, I'm going to change the cost function only so that my model learns that if it makes an error on class 1, that is going to cost it a lot more than if it's going to make an error on class 0, right? Because class 1 is your minority example, you don't want it to make an error on class 1, right? Because it has got smaller examples to learn from. So that's the technique that is called cost sensitive training. Now obviously the second idea is that use choice of algorithms.
Log on to GreyAtom's learning platform to unlock more free content. Subscribe to our channel and hit the bell icon for regular updates.